Hi, and welcome to a special episode of Operating Systems class. I'm recording this outside class because we don't get to meet on Thursday of this week. So I thought we would record a lecture and watch it online, and then we won't fall too far behind. Today, I'm hoping to continue talking about networking. I will get far enough with networking that we can run a little bit of code that lets two processes communicate over the internet using a couple of different protocols. We have a whole class in networking that's available to undergrads, and that'd be a great class to take. But not everyone gets a chance to take that. Doing a little bit of networking in operating systems, make sure everyone gets a little bit of experience with that. We've been trying to prepare for this since early in the semester. We've been talking about inter-process communication and an important way of designing programs as a set of cooperating processes. For a distributed application, we just need to be able to deal with the idea that those processes may not all be running on the same host. Fundamentally, we still want to be able to do the same thing. We want one process to be able to prepare a message, a sequence of bytes in memory, and then with help of the operating system and maybe a bunch of other devices along the way, we'd like that same message, that same sequence of bytes, to be able to get to another process running on a different, completely different host, maybe somewhere else in the world. We got some choices for how we could handle this. You know that you've got a device in your computer, you probably got a device, a network adapter, a network interface that lets you write out sequences of bits to a medium, like a network cable or a wireless, or write them out wirelessly, and you can receive data the same way. We could handle that device like we've handled other devices. We could let processes allocate it or request it when they want it, and then when they get a chance to use it, they could send and receive all the messages they want, and then they could just give it back when they're done. But this would be a bad way to deal with the networking hardware. There might be a bunch of processes on the computer that want to use the network at any one time. So we really need that device to be something that can be shared, kind of like we've done with a bunch of other devices like the hard disk. And for getting a message from one host to another, if those hosts are not directly interconnected, we're going to need help from a bunch of other hosts or devices along the way to make sure a message can make it from the sender all the way to the receiver. Doing this is easier if our network is small. A local area network is one where you've got a small number of devices and you can know a lot about how they're interconnected. This makes sending messages a lot easier because you can plan ahead for how the message is going to get from the source to the destination. Routing is how you choose the path that the message is going to follow. And on a small network, on a local area network, you can know enough about how the network's put together, or you can use some techniques like broadcast that may not scale to a larger network, but they would work fine as a way of helping with routing on a local area network. On a much larger network, like one that we might hope to communicate around the world with, we're not going to be able to make those assumptions. We might have a network that's got a very irregular topology. So when we send a message from one host to another, we might have to make a lot of decisions about how to get that message all the way from the sender to the receiver. And maybe even worse, we have to deal with a lot of potential problems along the way. We may have not just one process at trying to send messages, we may have multiple processes that are all using the same network from multiple endpoints, and that could create congestion on the network. That's where if you've got a single link and you've got a lot more traffic trying to go over that link than it can accommodate, then that traffic's going to back up. And you can buffer that for a while, but eventually your buffers are going to fill up and you're going to have to discard messages that can't make it across that connection if they're coming in too fast. And that may mean that the messages you send may not always make it to the receiver, at least without some additional help from software. You might also have to deal with a network that's heterogeneous, that's made of different devices, maybe with different architectures, different byte orders, and running different OSs. And you may have to deal with failures, both in the endpoints and in the interconnections in the network. For a large network, you can imagine that connections are continuously being added and continuously failing occasionally or being removed. So routing decisions are always going to be subject to change. You have to be able to figure out how to get messages from a sender to a receiver, even in the presence of a changing or a congested or failing network. And this slide just shows some of the stuff I was just talking about. If we're going to be able to let multiple processes communicate between different computer systems all over the world, we're going to have to figure out and agree on a lot of things about how that's going to work, both in the hardware they're going to use and in the software that's going to help manage that hardware, and the parts of the OS that are going to help with that. At the lowest level, we need to decide things like how we're going to build the physical medium that they communicate with, how we're going to build a cable that will connect to nearby computer systems, or how we're going to transmit communication through the air. Even if we figured this out, if we figured out how to build the hardware and get two computer systems to be able to communicate a sequence of bits between them, that wouldn't be enough to let, at least to give something useful to running processes. We'd have to worry about things like errors during transmission. Whenever you're encoding something into a physical medium, you have to worry about the possibility that you write out a 1 bit on one end, and when you read it on the other end, it might show up as a 0. You'd also have to worry about, well, what if the two processes that want to communicate are on hosts that aren't directly connected? Maybe there's not one wire between them that lets them exchange messages. Maybe you've got to get help from a bunch of computer systems along the way. If you've got multiple processes that are all trying to share the same connection, how do you manage sharing that? So we're going to need more than just the ability to write out a sequence of bits. That's okay. The rules for how we're going to construct and use our communication medium, that's really just the lowest level of software and hardware that we need to agree to. That's called the physical layer. And when you talk about things like Ethernet or 802.11 wireless communication, part of what you're saying is the rules for how you're going to use that medium. Within the OS, we're going to have to take that low-level mechanism for transmitting bits, and we're going to have to dress it up with additional software and rules that make it reliable, that make it shared, and that let us communicate across multiple links in a larger network. For the operating system, at least for us, this is something new. We've mostly talked about how one operating system would manage a computer. And to be able to do this, we've got to have multiple OSs, maybe by different manufacturers, that are all cooperating, that all agree to some standard for how they're going to communicate. The physical layer is the lowest level layer. It talks about rules for how you would encode a sequence of bits onto a physical medium. To be able to use this effectively, like I said, we're going to have to dress it up with some additional software. And the next layer describes some rules for how we're going to do that. The data link layer describes how we can take that low-level physical medium and break it up into fixed or variable sized frames, each of them with a little bit of additional data that let us use that hardware more effectively. Each frame will have a little bit of header information that makes the physical medium shareable, so you can tell what host that frame came from and where it's going. That would let you make at least local routing decisions. You could get the data, or you could get that frame to the particular destination it was headed to, as long as it was all on the same local area network. You could use that header information to detect low-level errors in transmission. If a bit gets flipped, maybe adding a checksum to the header would let you catch that kind of error. And when you talk about something like Ethernet or wireless communication, you're also talking about how this is going to work, how the data link layer is going to handle getting routing and delivering frames within a local area network. That's fine if you only want to communicate between hosts that are at a single site. But if you want to send messages around the world, you're going to have to worry about routing in a larger wide area network. And the network layer is what normally takes care of this. It takes the low-level frame delivery mechanism provided by the data link layer, and it adds additional header information to handle routing across multiple links. At this layer, we'll usually describe the data as being broken up into usually variable-sized packets. And within each of those packets, we can put a little bit of additional header information to handle routing across multiple networks or multiple links. Our favorite example of this is usually Internet Protocol. It's an example of a network layer protocol that takes care of routing packets potentially all over the world. I usually try to describe Internet Protocol IP as a best effort packet delivery system that has been deployed mostly worldwide. You drop a packet into it, and it does the best it can to try to get that packet of data to a destination system. It's got some additional header information that helps out without routing. Every packet has an address of a system that lets the packet make its way to the destination system. If you're using IP version 4, that's a 32-bit address. We've certainly strained that 32-bit system. So many systems are using IP version 6 now, where the address is a lot bigger, 128 bits. Every host on the internet has an IP address that identifies it so that packets can make it to that host. And instead of giving out those addresses randomly, they're organized so that we can have a chance at routing within a network of this size. You've probably noticed all the IP addresses at NC State all start out the same way. And if you went to another university, you'd see the same kind of thing. We give out IP addresses in an organized way so that if a packet is heading somewhere in the network, you can make routing decisions about which way to send it to get it closer to the host that it's destined for. So every packet is stamped with address information, IP address information about where it's coming from and where it's going, because of things we talked about before, because of congestion and potentially failures in the network. Packets that get sent out may not make it to the destination. That's why I say AP or IP is a best effort packet delivery system. It'll try to get your packet to where it's going, but not every packet is going to make it. So Internet Protocol as a network layer protocol will get packets between two hosts on the internet, but that's not enough to let applications use it directly. I may have 10 different applications that want to communicate. And if a packet arrives on my network interface, I need to know which application to give them to. So that additional behavior that we need is usually something that we get from the transport layer. It takes packets and it includes some additional header information so that we can tell which application should get them. Every application running on a system can have a unique port number. That's a 16-bit port number. And when you send out a packet, you can stamp it with the port number for the application that should receive it. And then as packets arrive, the OS knows which application to give them to. So it makes that part of the transport layer makes the network shareable by more than one process at a time. You can tell which process gets a packet that arrived because it's the one with that port number. Transport layer also takes the best effort packet delivery system offered by Internet Protocol and dresses it up with additional software and behaviors and header information to give applications something they can use. We talked about how, well, packets in Internet Protocol might get lost. Not everything that you send is going to arrive, and errors could be introduced during transmission. The transport layer adds some additional software to help catch those things and to give applications reliable communication if that's what they want to use. I'm being a little bit vague here because above the network layer, at the transport layer, we may have some choices in what kind of behavior we want to offer to applications, what semantics we want to offer that would let them write useful applications. And above Internet Protocol, there are usually two different things that we might do, or two different protocols that give applications different ways of communicating. And I've listed them here: Transmission Control Protocol and User Datagram Protocol, TCP and UDP. And these are, these let two different applications communicate in a way that gives them some useful behavior, but that hides a lot of the complexity that's going on underneath. When you're communicating, say, over TCP, you can send out what looks to you like a stream of bytes. That same stream of bytes will arrive at a receiver. You can think of that as logically something a lot like a pipe. Once you've established a connection, you can just send out bytes and eventually they arrive in the same order at a destination. But along the way, all the stuff that we've been talking about happens. Those bytes get broken up into packets. Those packets may get broken up into frames to hop across individual links in the network. They may traverse multiple links along the way, and the network layer may take care of getting them across the right link to get closer to the destination. And then when they arrive at the ultimate destination, they get pieced back together, maybe with some retransmission of lost data, so that the receiver gets the same sequence of bytes without having to worry about what happened along the way, without having to worry about this complexity. So here we're seeing some examples of the software and hardware layers we've been talking about. At the network layer, a typical example is Internet Protocol. It's built on top of data link layer technologies, and it provides, you can think of it as best effort packet delivery to hosts around the world. The operating system takes that best effort packet delivery system and it dresses it up with additional software and additional header information to try to provide useful semantics for the application. The problem is, typically different applications want different things. And that's why we have different transport layer protocols. If you want something that looks kind of like a anonymous pipe, a reliable stream of bytes from the sender to the receiver, then TCP will do that for you. It adds additional software and header information to Internet Protocol to make communication look like a reliable stream of bytes. Internally, it may have to retransmit some things. It may have to deal with congestion to give you that. But within your application, once you've established a TCP connection, you can think of it a lot like we do a anonymous pipe. But if that's not what you want, there are other transport layer protocols. UDP takes the same mechanism provided by IP and it dresses it up differently. It adds different header information to provide what looks like a delivery of whole messages, a message at a time, not just a stream of bytes. But it doesn't necessarily guarantee reliability. Depending upon the application you're writing, one or the other of those protocols might be more suited to what you're doing. And that's why if we look at the top layer, those are called application layer protocols, because anything you want to do on top of what's provided by the transport layer, you're going to do that within some user process. So you can add additional rules for how you communicate, additional header information within your application, but you're going to be doing that with software in the process. That's not going to be the OS's job. Here I've listed some standard application layer protocols. Many of these you've probably heard of. And you can see some of these are typically used on top of TCP. Others are typically used on top of UDP. We'll see the one in the middle, remote procedure call, at the end of this material, and it can run on top of either, and there might be reason to prefer one or the other of those. Each of these is using a 16-bit port number to dispatch messages to individual applications. That's how the transport layer protocols, at least TCP and UDP, that's how when a packet arrives, the OS knows what application to give it to. It's stamped with a particular port number. And for these standard protocols like SSH or HTTP, they're expected to be running at these particular ports. You don't have to run them at that port, but if you're running them at the standard port, for HTTP, you're going to be using port 80. For SSH, you're going to be using port 22. All of those low numbered ports are called well-known port numbers. They're associated with a particular application that's expected to use that. Now, we mentioned that UDP is it provides delivery of whole messages to an application. It's built by taking the best effort packet delivery system of UDP and adding additional header information to take care of routing or getting whole messages. For UDP, they call them datagrams, getting whole datagrams from a sender to a receiver. Within the header, it adds a port number so that when that datagram arrives, it knows which application to give it to. It doesn't just make it to the host, but it can make it to a particular receiver on that host. And it adds some additional header information to detect errors within the body of the datagram. So if something gets corrupted during transmission, UDP can be expected to detect that. What it doesn't add is reliability. It's built, UDP is built on top of IP's best effort packet delivery system, but it doesn't add retransmission, or it doesn't include retransmission of lost information. That means you might send out a UDP datagram, and if that gets lost, or if part of it gets lost in transmission, maybe because of congestion, it won't guarantee that it arrives at the receiver. That may seem like a hard protocol to use within your application to be able to tolerate lost messages. But for some applications, that makes a lot of sense. For multimedia applications, if you have the choice of retransmitting lost audio information or just going on with whatever comes after it, it might make sense to just keep playing out information rather than making sure you retransmit things that maybe should have played a second or two in the past. So some applications are well suited to a model like UDP. I've got an example here that tries to show how you might use UDP within an application, and we'll see a Java program that works like this later on. So let's say we've got two processes running on two different hosts. That's this bluish circle I put in each of these. They want to communicate over UDP. There are probably a bunch of other processes that are using TCP or UDP on those hosts. So I've drawn those with port numbers that they might be expected to be using. If you want to communicate on UDP, each of your processes is going to open up a UDP socket, and you're going to ask for a particular port number so that when messages arrive at your host, those really as datagrams arrive at your host, they can get dispatched to your particular process. So here I made up two port numbers. We'll pretend our processes are running at each of those port numbers. I picked two different port numbers so that if I ran these two programs on the same host, they wouldn't conflict for those port numbers. But they're running, here I'm pretending they're running on two different hosts, so that doesn't matter as much for this picture. So when one of them wants to send a message, it'll prepare a UDP datagram and it'll send it, and it'll make its way through the internet and hopefully arrive at the destination. UDP doesn't guarantee that that message will get delivered, but let's say it gets delivered. That message arrives at the receiver. It's stamped with the receiver's port number, so it gets delivered to the process that's getting UDP datagrams at, in this case, port 9875. It might send back a reply to that message. It'll prepare its own datagram, send it out through the internet. It'll make its way through the internet, eventually, hopefully arriving at the destination. And if it's stamped with the receiver's port number, the OS on the receiver will deliver it to the receiver process. And processes can communicate, sending datagrams back and forth with each other. In fact, you could have any number of processes that are exchanging datagrams. Once you open a datagram socket, you can send a message or send out a UDP datagram to any host and any port number that you want. There's nothing special, at least as far as these two processes are concerned, there's nothing special about who they're talking with on the other end. It's just who they try to send that datagram to, what host they're sending it to, and what port number on that host. Since UDP doesn't guarantee delivery of datagrams, it's possible that any of these datagrams might get lost. And that's something that your application is going to have to deal with. You could handle this by retransmitting the datagram itself if it never seemed to arrive. Or like I tried to say a couple of slides ago, some applications are well suited to this model. Now, if UDP doesn't give you what you want, maybe TCP will. TCP takes the underlying best effort packet delivery system offered by IP, and it dresses it up to make it look like a reliable two-directional byte stream. Either side of the communication can send out a sequence of bytes, and kind of like an anonymous pipe, they arrive at the other end in the same order. It takes that sequence of bytes and breaks them up into packets, sends out a packet every so often, and it tries to make sure those packets arrive by sending back acknowledgements. The receiver says how many bytes they've received so far, and if the sender doesn't get an acknowledgement soon enough, they'll retransmit that automatically. So, and then at the receiver end, they paste together all the packets that as they're received and give the application the bytes in the order that they were sent, even if some of them had to get retransmitted along the way. An important thing it does is it tries to pay attention to congestion. As it's sending information, if it notices that it's losing more and more packets, it'll actually slow down rather than trying to transmit even more. And if there are problems of congestion in the network, as long as everyone is doing this, that should help to reduce the congestion, and then everyone can send at a rate that lets their packets get through. How does it slow down the communication? Well, we've already seen this kind of thing. We saw it in bounded buffer. Whenever an application tries to send, if it's sending at a rate that's too high for what we believe the network can handle, the OS can just make the application block and then send, and then wake it up a little bit later and let it send more data. So it uses the same mechanisms that we used when we were implementing a similar thing for bounded buffer. I've got an example here that shows how two processes could communicate using TCP. And here I've mixed together a picture that shows how you could think of this as working, and code from two examples that are posted for this. So we're going to use a client and a server to communicate with TCP. Even if you just want to communicate between two processes, one of them has to take the role of the server to get the communication started. So I've got the code and the example for the server over on the right, and I've got code for the client over on the left. We're going to be using an API for C programming, and this is available on a variety of systems, Unix systems and other systems. So when we talk about the sockets API, that's a programming interface that there's a good chance you might get to use no matter where you're doing your programming. All right, so we've got a client and a server that need to communicate. You can see the client is going to use its command line arguments. The server doesn't need those. When the server starts up, we're going to call a function called getAddrInfo. This does two things. It does DNS lookup for host names. We'll use that with the client, but for the server, it uses it to find out what communication interfaces are available and to get the right parameters to open a socket to communicate over those interfaces. You might have a system that's got multiple network interfaces or other ways it communicates. And this getAddrInfo is meant to let the programmer use all of those the same way, no matter how the communication might be going on internally. So we go to getAddrInfo, and I highlighted the important parts here. You're going to prepare a struct, and you're going to fill in some fields about how you want to communicate. You can see here, I'm asking to communicate over TCP. And then when I call getAddrInfo, I get back a list of addresses. I'm just going to use the first address on that list, the first interface. Then I call socket. This is part of that sockets API I was talking about. This makes what we would call a server socket. It's not directly going to communicate with the client, but it's how the communication gets started between this client and the server. You can see I'm using parameters that I got back from getAddrInfo on the previous slide. So the server makes a server socket, and then it calls bind to associate that socket with a particular address on the host. And then it calls listen, and that makes the socket negotiate for connections with any clients that want to come along and connect with it. I mentioned earlier that even if you just want two processes to communicate, one of them has to take the role of the server to get communication started. And this is why one of them is going to have to sort of be open for business. They're going to have to sort of invite connections from clients, and they do it by creating a server socket, binding it to a particular address, and then listening on that. And then that's what the client is going to use to really get communication started. So once the server does this, it calls accept, and that makes it wait for a client to connect. So after the server has done all of that and then called accept, the client, or at least when we run the client, it'll start by calling getAddrInfo just like the server. And you can see I filled in a struct with some information about how I want to communicate with the server. I want to communicate over TCP. And for the first parameter to getAddrInfo, you can see I'm taking my first command line argument. I'm going to use that to provide a name for the host that the server is running on, and getAddrInfo will convert that name, that human readable name, to a network address, either a 32-bit IP address if you're on version 4, or a 128-bit address if you're on IP version 6. So the client's going to call getAddrInfo. That'll fill in a list of AddrInfo structs. It's just going to use the first one, same policy as the server. It'll use the first one to make a socket, and then it'll call connect. This socket that the client made here is for communicating. It's not for inviting new connections. It's actually how we're going to send and receive bytes. And this connect is what's going to get that started. When it calls connect, it's going to send a packet, at least internally. When you call connect, it's going to send a packet to the server at the server's port number. When the server opens its server socket, it invites connections at a particular port number. Here I just made up a port number and put it there. So when the client tries to connect, internally a packet gets sent to the server saying I want to connect. The server sends back a reply, and then the client replies one more time. And then once this is done, the server is ready to communicate with the client. In fact, this is when it returns from accept. We mentioned earlier, when it calls accept, it just waits, it blocks until a client connects. When that third packet arrives, or that so backing up, client sends packet, server sends a response. You don't have to do any of this as the application, but this is happening inside the OS. Client sends a request, server sends a response, client sends back a response, and that's when the server returns from accept, and it gets back a socket for communicating with the client. So it gets back a socket in the connected state, and that's one that it can send and receive bytes over. So now the client and the server both have sockets that they can use to send and receive data. So at this point to them, this socket looks like a reliable two-way byte stream. It kind of looks like an endpoint, or it kind of looks like a anonymous pipe, except you can send and receive bytes in both directions. In fact, the sockets that the server got, that the client got when they called socket and the server got back from accept, they work just like file descriptors. You can send and receive using the same read and write calls you would call for reading and writing a file. Or there are more special purpose functions. There's a send and receive that has one additional parameter that lets you say more about how you want to communicate. If you're communicating on UDP, you're going to be using system calls send to and receive from, because with UDP, your UDP socket isn't connected to anything. It can send out UDP datagrams to anywhere. So every time you send a datagram, you have to say where it's going. And whenever you get a datagram, you'd like to know something about where it came from. So these two calls are a little more specific for UDP communication. for our sample program, so we've been looking at snippets of code that show how we're actually going to use these sockets. In our sample program, once the client and server each have a socket that they can send and receive data on, a connected socket, we're just going to send a megabyte of data from the server down to the client. And that's what I tried to draw in this picture. We're going to send it in 64 kilobyte chunks. So over on the right, you can see the server's got a loop. It's going to keep sending data until it's sent a megabyte. That's what total is in this example. It makes a buffer that's 64K in size. It doesn't even put anything in the buffer. It essentially sends a buffer full of uninitialized data, because I don't really care about the data I'm sending here. I just want to see, that it arrives, and I want to see how fast it arrives. So every time we send a block of data, I print out a message and I count it. Oh, and one detail up here, whenever I'm sending, I send either a whole block of data, or if I'm close to the end, of that megabyte, I send however much is left before I hit that megabyte mark. Over on the client end, we're doing the same kind of thing, except we're reading. I loop until I've read a megabyte of data. I make a buffer for receiving up to 64K, and then I read as much as I can, or I try to read as much as I can, either a full buffer size or whatever remains in the megabyte, and then I report how much I read each time. Notice here I'm just using the plain old read and write system calls that you would use for reading and writing from any file. Once the megabyte has been successfully sent, both the client and the server are done. Here we can just call close to get rid of these resources. On the client side, they can close the socket that they made to communicate with the server. On the server side, you've really got two sockets. You've got the one that you use, the server socket you used to listen for connections, and then you've got the one that you got back from accept. Close will work on both of these. So I close the socket I was communicating over, and then this server is not going to talk to anyone else. It just terminates after this. So it closes its server socket at that point. I got an example program. It's the same one we've been looking at code on. Let's go try out that example program. So here I've got two terminal windows running on, well, this one's running on my laptop, and this one's running on a machine at Baylor University. I used to work there before I came to NC State, and I still have an account on a machine there. So I like to run this program on that machine because it's pretty far away from NC State's campus. Interestingly, I'm traveling this week, so I'm even further away from NC State's campus. I'm in Bangladesh, so I'm pretty much on the opposite side of the world from the machine here at Baylor University. So I'm going to run the client here at Baylor University. The client didn't take any, I'm going to run the server at Baylor University. It didn't take any parameters, and it's just a TCP server is what we called it. And this example should be posted with our Moodle examples. All right, so when I did that, it did all the code we just looked at. It called getAttr_info, it made a server socket, it did bind, it called listen to wait, or to tell the OS to negotiate for incoming connections, and then it called accept. And right now it's waiting in that accept call for someone to try to connect to it. Over here on the client side, remember the client, it was called TCP client. It expected a parameter that's the host name, and then when it called getAttr_info, it converted that to an IP address. So my host name is, it's a machine called Earth at Baylor. And then when I hit enter, the client's going to call getAttr_info, it'll make a socket, and it'll call connect, and then internally, these two processes with help of their OSs will negotiate for a connection. And then once that client successfully connects, the server is going to start pushing data as fast as it can to the client until it's pushed a megabyte of data. And I don't know if I mentioned this, in the code we looked at, I get a little printout every time I get a new buffer worth of data. So I'm going to hit enter on this. Oh, sorry, I forgot the U at the end of edu. Let's try that again. All right, so you can see when the server sends, it was sending in 64K or kilobyte chunks, and that's what I get. Every time it sent, it looks like it successfully sent a kilobyte worth of data, but the receiver didn't get the same data, or sorry, it didn't get it in the same units. It would call read and it might say, oh, I've got room for 64K of data, but maybe that hasn't all arrived. The OS might give it the data it has as soon as it can, and then the client just goes back and calls read again. So you can see here as this communication made its way through the network and arrived at the client, it kind of arrived in smaller pieces than what got sent. And if we scroll back, you can see, yeah, the amount of data it got with each call to read varied from call to call. This is what, it was in my slide, but I forgot to mention it. This is what I meant when I said TCP doesn't respect message boundaries. When you do a write or a send, you'll send out a certain amount of data, but when the receiver does a read, it may not get exactly that same amount of data. If you want to think of your communication as being broken up into messages, and you probably do, then you're going to have to add code to worry about that yourself. The API we just looked at for programming with TCP in a C program, the sockets API, is complicated. It's got a lot of functions with a lot of parameters. For those, I just expect you to know in general what each of those functions is responsible for. It'd be hard to code that from memory. The Java API is way simpler, and it is something you easily could memorize and use. I could probably still write network communication code in Java, mostly from memory. In Java, we'll show what it takes to communicate over TCP and a little bit of UDP. We saw that in the C program, the server has to make a socket that it just uses for getting connections, and then another socket gets created when someone actually connects. In Java, these are done with two different classes. The server socket makes a server for accepting connections. Halfway down the slide, I show how you might use it. You would call the constructor, passing in the port number you want to use to listen for connections, and then you would call .accept to wait for someone to connect. The plain old socket, or java.net.socket without the server in front, that's a socket used for communicating. When accept returns, it gives you an instance of that, and that's the socket that you would use to send or receive bytes to a connected client. On the client side, you just have to call the constructor for the socket class and pass it the name of the host, or you can pass in its IP address and the port number the host is listening for connections on. This will internally, it'll call socket, it'll call connect. And then once those succeed, it'll give you back an instance of socket. And then once the server has done these two things and the client has done this, you got a socket that's ready to communicate, to send and receive sequences of bytes. There's also a datagram socket you can make to communicate over UDP. And we'll look at an example of both of these. Back to our examples. I've got a recording of a Zoom video. I've got for TCP in Java, I've got two programs called example client and example server. Let's look at the client side communication first. It'll be a little bit simpler. So in my main method, I'm expecting as a parameter the host name of the server. So I call socket, and I just go get the port number that the user is using. There's a field in the server object for that. So I just go look at that field. This will connect, or it'll try to connect and give me back a socket. If it fails, you can see a lot of this code is mixed in with try-catch blocks. There are exceptions that explain or that tell you something about what went wrong if one of these calls fail. So you can see I've got a try block up here. Once I'm successfully connected, my socket is really a wrapper for streams for sending bytes and receiving bytes. So I go get those two streams. And then what I'm going to communicate with the server about is I'm going to send it a string. I go to the user and get them to type in a message. And then I turn that into a sequence of bytes. There's a method on string that'll just encode it as a sequence of bytes. And since that's what sockets communicate, that lets me actually send it over the socket. So I take the output stream and write out that buffer. And then I do a flush on the buffer. I might be able to get away without this, but remember we talked about as you send sequences of bytes on TCP, those get broken up into packets and sent to the receiver. It'll, as you're writing out stuff, it may break that into multiple packets. Once you're done preparing a message, Flushing it tells the OS that you want that sent out to the socket before you continue running, and may not be received before you continue running. But this flush says don't wait for more data to be written to the socket. Go ahead and try to write out everything you can. And then so I've sent a string to the client, to the server, encoded as a sequence of bytes. It's going to send me back another string encoded the same way. So I read a sequence of up to, I've got room for 1024 bytes. I try to read that, and then I'm expecting it to be a string encoded as a sequence of bytes. There's a constructor to get that string back. I get it back from the server, and then I just print it out, and then I'm done. I close my socket, and then the client's done. Over on the server side, if we look at example server, the server is going to, well, it's got a port number. That's the one we talked about before. I just made up a port number for the server to use. It calls server socket and says I want to listen for connections at that port number. And then over and over, it's going to try to accept a connection from a client. That gives it back a socket it can use to send and receive bytes. It gets the two streams out of that. And then we're counting on a client doing what we just looked at, getting a message and wrapping it up in getting a message as a string and turning it into a sequence of bytes. So we get that array of bytes, turn it back into a string, and then we send it back to the client with a little extra decoration. We print out a message. This is just diagnostic. But then we take the message and we wrap square brackets around it, just with some string manipulation. Then we turn that into an array of bytes and write that back to the client and flush it out to say, oh, don't wait for me to send anything else. Go ahead and send this to the client. And then the server's done talking to this client. It closes the connection to that client, but it keeps looping, waiting for additional clients. So this server could talk to client after client, one at a time as they connect. It never really closes the server socket. You'd have to hit Control-C to make it terminate for that. So I'm going to run the client up here, Java example client, I'm going to run the server up here, Java example server. And down here in the client, let's run, or down in this other window, let's run a copy of the client, Java example client. And remember, it wanted the host name of the server. Here, I'm just running these both on my laptop. So I'm just going to give local host as the host name, and it'll still use all the same communication code, but it won't really be going out on the network. It'll just be getting all the data delivered to another process on the same host. But the nice thing is the same code would work even if they were running on different hosts. All right, so I hit enter. At this point, the server, I should have said it was, until I did that, it was blocked waiting for an accept. When I did this, the client connected to the server, and now the server's waiting for data to receive from the client. The client's just waiting on me to type a message. So I'll type, I'll hit enter. The client wraps that up in a, it turns it into an array of bytes, sends it to the server. The server just prints it out so we can tell something happened. Put square brackets around it, turns it back into an array of bytes and sends it back to the client. And then the client prints that out. The server's doing this for client after client. So if we ran this program again and said some real message, then the server would accept our connection and communicate with us. I want to show one thing that's a natural consequence of how TCP works. If I go up here and kill the server with Control-C, now there is no server. And if I go down and run the client, you can see I don't even get to the prompt for a message. The client tries to connect to the server before it asks the user for a message, and that connection fails. Remember, when you try to connect a socket, there's an exchange of messages just to get the communication started. And up here, there's no one to exchange messages with. So that attempt to make a connected socket fails. So we've also got an example of communicating using UDP with Java. The API there is a little more complicated than the TCP example, but it's way simpler than it would be if we looked at it in C. We've got two example programs, UDP client and UDP server, and together these do something similar to the program we just looked at in TCP. The client gets a string from the user. sends it to the server. The server gets the string, wraps square brackets around it, and sends it back as a datagram to the client. Let's look at the client first. All right, so there's the port number the client's going to run on. I just made up a port number for that. The client, well, there I'm making a datagram for when I eventually receive a response from the server. I could probably move that later in the code. I get a message from the user, and then I make a datagram socket. That's for sending out the message and eventually receiving the message. Once you make a datagram socket, you're in business to send and receive messages to any other host on the network. I don't have to connect. I just, for every message, for every datagram, I say what host it needs to go to. The client's expecting a command line argument that's the name of the host you want to send a message to. Java has a mechanism for name resolution for this. So I turn that name into a network address. And then I make a datagram packet for sending a message out to the server. A datagram is going to be not just the data you want to send, but some information about where that, what host that data needs to go to and what port it needs to be delivered on the host. And that's all wrapped up in this datagram packet. You can see for the parameters, I have to tell it the data I want to send and the address of the host it's supposed to go to and the port number on that host. And then when I send it, that datagram makes its way through the network, hopefully eventually getting to the receiver. And then the client tries to get a response. It should be a string containing the message I sent with square brackets around it. So I receive, using that packet that I showed up at the top, another datagram packet. I go inside that, I get the array of bytes out of it and make a string with that, and then I print that out. And then as the client, I'm done. It looks like I don't close my datagrams socket here, but of course it'll go away when the client exits. Over on the server side, the nice thing is the server doesn't have to make a server socket for listening. It does almost the same thing as the client. It makes a socket, and then it responds to any datagrams that arrive on the socket. It doesn't have to negotiate for a connection before it can do that. So the startup cost is a little bit reduced. TCP, we had to wait for 3 messages to make their way through the network. Here, we don't have to wait for that. The server's going to run at a slightly different port number. This lets me run both of them on the same host, and that's what I'm going to do here. For the server, the first thing I'm going to do is receive a request from a client. So I make a datagram packet just for receiving that, well, not a request, but receiving a message from a client. And then over and over, I wait for someone to send me a datagram. I go get the string out of that datagram, or I go get the byte array and turn it into a string. I print out a diagnostic message. I prepare a response. I'm going to send it back to the client. I prepare a datagram packet for going back to the client. And the datagram I received has additional information. It's not just the data payload. It also knows what host it came from and what port that host was using when it sent it out. So I can go into the datagram packet and get those out. And I can use those as the destination for my response. So when I make my datagram packet that's going back to the client, you just reuse where its datagram came from. I send that out, and then I go back to the top of the loop. The server is going to respond to client after client, but it's going to respond whenever it receives a datagram. It's not going to have to wait to connect with each of those clients first. And then so the server just keeps doing that until you terminate it. So let's run the server up at the top, UDP server. And then let's run client down at the bottom, UDP client. So the server has made it up at the top. It's made its UDP datagram, and it's just waiting. Sorry, it's UDP socket. It's datagram socket. And then it's just waiting for a datagram to arrive down at the bottom. We're going to run the client. Again, I'm like before, I'm running both of these on my laptop. So I'm just going to say localhost for the server. When I hit enter, the client prompts me for a message. I don't think it's even made its datagram socket yet. I'm going to say hello. And when I hit enter, it'll wrap that up in a datagram, send it to the server. The server prints it out, wraps square brackets around it, makes another datagram, and sends it back where the first one came from. And the client prints that out. And you can see, just like our TCP example, the server here is just accepting datagram after datagram and sending back a response. However, unlike our TCP example, if I sneak up here and kill the server and then try to run the client again, it hasn't. At this point, the client has just prompted the user for a message. It hasn't tried to establish a connection with the server because we don't have to do that with UDP. So I'll just make up a message and hit enter. It sends out a datagram, but no one ever receives it. And because I never had to connect with the server, I don't really have, at least the way I've written this, I don't have any mechanism for knowing that no one received that datagram. I'm just stuck waiting on the response datagram. And this is the kind of thing that you have to think about if you're writing something with UDP. Any of your messages, any of your datagrams might not make it to the receiver. For some applications, that's not necessarily a problem. You can work around that. But here you wouldn't want to just be stuck waiting forever for a response that's not going to make it. Here, the client can't even tell that the server's not there. So the sample code that we've looked at gives us some ability to write a little bit of networking code in C or in Java, and we're going to get a chance to do both of those things on homework assignments. The mechanisms we've looked at so far, if you're writing a distributed application, it'd be very clear that it was a distributed application. Your code would have a lot of sends and receives mixed in. You might have to worry about failures in the communication. So this doesn't really, this lets us write a distributed application, but it doesn't really hide the fact that it's a distributed application. It's going to take a lot of work from the programmer to write an application that runs across multiple systems. There are a variety of efforts to try to reduce that work and make it so writing a distributed application doesn't have to be that different from writing an application that runs on a single host. And the next thing we're going to look at, remote procedure call, is typical of a lot of those efforts. Remote procedure call tries to let you write a distributed application, but it hides the boundaries between systems in something you would normally be using anyway, in procedure calls, in function calls. Remote procedure call is a mechanism that lets you, or that tries to make it easy to take a program and break it so that a subroutine can live on one host and the code that calls it can live on another host. And most of the work for calling that remote subroutine is done for you. It's done by compiler tools so that all the communication gets written automatically. All you have to do is describe the interface to that remote procedure, and then hopefully the hard work of writing a distributed application can be automated. This is really an example of a mechanism for computation migration. We talked about that early in the chapter. Having code that can be invoked can be accessed from one machine, even though that code actually executes on another machine. It would be a way of letting us use remote resources by wrapping up the access to those resources in something like a remote procedure call. So again, remote procedure call tries to hide the distributed parts of the application, and in procedure calls, and it tries to make the programmer's job easier by having tools, compile time tools, that automatically write that code for you. The way a remote procedure call is going to work is when you call that remote procedure from your client, over on the left, it's going to look like you're calling a plain old subroutine, a plain old procedure within your program, but you're really calling, when you call it, you're really calling a stub, a function that's made to do the job of the procedure, but to hide the fact that the real work is going on another machine inside the stub. And to make it clear, that stub is the kind of thing that one of these compile time tools would write. If you say, here's how my remote procedure is supposed to work, a tool ought to be able to write a stub for you that lets you use a remote procedure just like you would use a local procedure. So you call the client on the client side, you call this client stub, it takes all of your parameters, wraps them up in some network communication, maybe wraps them up in a datagram, and sends them off to the server as a request. You didn't have to write that code. That code hopefully gets written for you automatically. Over on the server side, you're going to have a piece of software that's just waiting for remote calls. It responds to remote invocations as they arrive. When a request comes in, it unpacks the parameters and then calls just a regular old function. There on the server side, you have to write the regular function, but hopefully you don't have to write this code that does the job of waiting for call after call. The code you're writing will hopefully look mostly like any other function. It's accessed by a piece of code that's waiting for remote invocations over and over. Your function does whatever it does. It maybe returns values to the caller. The generated code will pack those up. Any changes to the parameters, if say they're passed by reference parameters, those will get packed up also, and those will get sent to the caller. It'll unpack those results and return them as if the subroutine executed locally. So hopefully this code in the middle, we don't have to write. The code on the outside, and I didn't show the client code because I ran out of room, but the code that makes the call and the code that implements the call, we'll have to implement those. But hopefully that'll be as easy as writing any other subroutine. Another nice thing about remote procedure call, I mean, one nice thing is it hopefully hides a lot of the complexity for the developer, and it can be implemented. You may have seen this from the picture before. It can be implemented on top of TCP or UDP. Implementing it on top of UDP has the advantage that overhead is much lower. You don't have to negotiate for a connection every time you want to call a remote procedure. But the hazard of that is whenever you send out a request, if it's based on UDP, that request might get lost. And that's what I'm trying to show here. You send out a request and maybe it gets lost and the remote procedure never gets invoked. Well, the stub can be smart enough to try to handle that. If it doesn't get a response within a certain amount of time, it can automatically resend the request until it gets a response. So this would let us use something like UDP with some reliability built in that we didn't have to write. There's a problem with doing it this way, though. If you resend a request just because you didn't get a response, you don't really know if the request got lost or the response got lost. You just know that you kept making the request until you were guaranteed the function got called. But maybe this first time, when you send out a request and didn't get a response, it was the response that got lost. And if you make that request again, you're really calling the subroutine a second time. This, I guess it gives us a reason to talk about procedure call semantics. When you call a procedure, well, normally you expect if you called it once, then it executed once. And we got a name for that. We call that exactly once semantics. And until today, we probably haven't had to worry about other types of semantics. But what we just talked about, we'd probably describe as at least once semantics. Backing up a slide, if you call a subroutine and internally, it might actually get called a couple of times because of loss of a request or loss of a response. Then when you call it, if that call executes successfully, you don't know if it got called once or more than once. That's, like I said, we'd call that at least once semantics. That is the kind of semantics you might naturally get if you implemented RPC over UDP. And I was going to make the point that's something that you can design for. You can design a interface where you could tolerate at least once semantics. If you're trying to design that, the thing that you need to keep in mind is all of your subroutine calls have to be idempotent. Calling them once should have the same effect as calling them 100 times, as long as they have the same parameters. And that really is a design choice for how you build some APIs. For example, if you had a request, if you had a subroutine that incremented a value, that wouldn't be idempotent. Calling it 5 times would increment it 5 times. Calling it just once would increment it once. So it wouldn't have the same effect. But if you could design it so instead of saying increment this value, your subroutine said, we'll set the value to a particular value. Set it to, it was 5, set it to 6. That would have the same effect, but that would work even if you accidentally called that subroutine multiple times. Calling set this value to 6 a bunch of times will still leave the value at 6. So we would say that design for an interface would be idempotent. So with remote procedure call, we might have to design for things like at least once semantics. At the bottom I listed, you could also implement a remote procedure where you got at most once semantics. It's just, you just build the stub differently. Instead of retransmitting a request until you get a response, you could just send the request once, and if it got lost, you could just return immediately. In designing a distributed application, we've got some choices for how we sort of assign responsibility to the different parts of our application. A common technique is a client-server model, where you might, and that we've used that a lot this semester. In fact, the way we've talked about a lot of these communication APIs kind of naturally invites a client-server model. We could have a server where shared resources reside, and then clients that access those shared resources by sending requests to the server or servers and receiving responses. So really in this model, the ability to share things is managed by having one or a small number of servers that provide access to those shared things. I guess a disadvantage of this model is that can put a lot of load on a server, maybe one with limited capacity, especially if the number of clients can grow unbounded. We can have some choices in how we design a distributed application that try to help us manage this. Within an application, I'm trying to draw this on the right here. You've got certain code that you wrote that does what the application does, but that code's usually divided into areas of responsibility. You might have some code that shows a user interface to a human user. You might have some code that has persistent storage for that application. And breaking the application into layers like that gives us opportunities to divide responsibility between the client and server, and maybe put more responsibility on the client. That would help reduce the load on the server and could let our application scale up to more concurrent clients. On one extreme, we could take all the code for our application and put it on the server and really have a client responsible for almost nothing. We call that host-based processing. The client is just an access point for the computing on the server. This is what we're doing on homework assignment 5. We're writing a distributed application, but the client is so simple that we're using a generic program, NC, for that. The client just echoes whatever the server prints out and sends whatever the user types to the server. We could, so the disadvantage is the server has to do everything there. We could reduce the server load by putting at least the user interface code, the presentation logic on the client. And then the client does all the work for showing the user an interface. But whenever it needs to actually do something in the application, it's going to have to send a message to the server. We could try to farm off more responsibility to the client by putting really all of the application logic and access to persistent storage on the client. And then the server could just provide access to that persistent storage, maybe an interface for accessing a database. A nice thing about that approach is, well, databases already have mechanisms for accessing them remotely. So that would let us put all of the logic except the database access on the client. And then I guess I should have said the same thing for this. There are models that let you write an application with a user interface that runs on a different system. So if we break the application here at the presentation logic, or at the database or persistent storage access, we'd probably have a lot of help from existing software to do that for our application. But if we're willing to break an application within the application logic, have some of the application logic that gets to execute on the client and some of it that has to go to the server, that gives us usually that gives us a chance to write a more efficient client. We can farm off more, a more efficient application. We can farm off more responsibility to the client. And if the client knows something about what our application is doing, it may be able to cache values, so it only contacts the server when it has to, reducing network communication and latency. That probably could give us the best performance, but there you're going to have to do a lot of that yourself. There's not going to be as much existing software that makes that partitioning of your application automatically. All of these are mechanisms to try to reduce the load on centralized resources. However you do that, having one or a small number of centralized servers is going to limit the scalability of your applications. There are other approaches to designing distributed applications that try to reduce the load on a central resource. Peer-to-peer approach tries to spread responsibility for what the server might normally do, spread that among the clients instead. So as more clients participate, they also provide more computing power or more storage space that can provide services to all the other clients. They're also, for some applications, they're a way of expressing them, their logic as transactions that can be automatically distributed among multiple hosts or multiple clients, so that you can reason about how your application is distributed without having to figure that all out yourself. This gets us to the end of our networking chapter. We've hopefully very quickly tried to learn how to, learn some basic ideas about what a distributed system might be like, learn how to write a little bit of code that might run in a networked environment, and then talk about ways that existing software could simplify the design and implementation of our distributed application. Thanks for your attention. I'll see you in class soon.